Hello from CERN in Geneva, and welcome to the launch of Sparks, the Serendipity Forum. I'm Bruno Giussani. I'm going to be your host today, and we're here to discuss science and innovation across scientific disciplines with guests from CERN and from around the world. We are in the CERN auditorium. We are safely distanced. The whole team is wearing masks. First, what is Sparks? It's going to be a 2 days annual event, which is going to take place for the first time here in Geneva next September. A public part and a scientific specific part. Today we are launching it, announcing it. We are laying the scene for the discussions to come. The aim is to bring together scientists from different fields, together with business leaders, with decision makers, the wider public, ethics specialists, and others, to try to discuss some of the biggest questions confronting us. I'm joined now by CERN's Director of International Relations, Charlotte Lindberg-Warakaule. Welcome. Tell us what the goal of Sparks is.
Thank you very much, Bruno, and thank you for being with us. As you know, CERN is the world's largest laboratory for particle physics. Here, thousands of brilliant scientists come together in order to study and explore the fundamental constituents of matter and how they interact, and through that, understand better how our universe has developed. And we want to bring this spirit of innovation also to discussions around cutting-edge themes in science, in technology development, in engineering, and in mathematics. Discussions that are important, crucially, of course, for CERN, but also for society more broadly. We want to focus on activities that are of relevance to what we do in particle physics, but also cut across to other scientific fields and discuss themes that bring all of us together, such as, for example, artificial intelligence. So it's an opportunity for us as a scientific community to learn, but also to engage more broadly with society.
So today, as you said, the focus is going to be on artificial intelligence. That's a field that's moving very, very fast. It's complicated. So maybe let's start with a primer. What is artificial intelligence? How does it work? We have a short video created by the Royal Society in the UK. It's a 2-minute video. Let's watch.
These are exciting times for artificial intelligence, or AI. But what is AI? AI is the science of making machines smart, using algorithms to allow computers to solve problems which used to be solved only by humans. AI already powers search engines, online shopping recommendations, and digital assistants. Radiologists can use AI to calculate the exact shape and volume of tumours, revolutionising treatment. Astronomers use AI to find and evaluate exoplanets in distant solar systems. And unhappy motorists are using it to discover if they can overturn parking fines. The possibilities of AI are endless, from fraud prevention to developing new strategies to address climate change. AI technologies today are brilliant at analysing vast amounts of data to learn to complete a particular task, a technique called machine learning. But AI is not good at transferring what it's learned from one type of task to another. Learning abstract concepts and one-shot learning, where a general rule is learned from a single experience, the sort of broad intelligence humans excel at. But even without achieving this broad intelligence, AI is raising questions. How might AI affect work? People will still be needed in the workplace, but jobs and roles are likely to change as some tasks become automated and new jobs are created. There is a risk that, at least in the short term, this could increase inequality if some people are disproportionately affected and benefits aren't widely shared across society. And what about social equality and fairness? Bias coming from AI systems, even if unintentional, could disproportionately affect some social groups, influencing anything from job prospects to treatment by the justice system. Technology can play a role in helping to manage bias, but people need to address big questions about how society wants to use AI. Technology with AI at its heart has the power to change the world. The more of us that engage with shaping its development, the more chance we have to ensure a better, fairer future with AI.
So that's the big general picture about AI. Today we're going to discuss a narrow slice, AI and scientific research. Charlotte, the theme for Sparks 2021 is Future Intelligence. Why was that chosen?
The flow, the analysis, and also the interpretation of very large amounts of data is, of course, a core strength of CERN. And as we attack ever more complex questions in particle physics, we also need to rely on the latest developments when it comes to computer technologies, and that, of course, also includes artificial intelligence. So it's an area of great interest to us and for the future of our field. And at the same time, CERN is uniquely placed also to bring together communities of big data and artificial intelligence. And this is why we focus here on future intelligence in this first edition of Sparks. Of course, we have lots to learn from other fields. That's why this is all about exchange and engagement. We also believe that CERN brings particular expertise and knowledge to this discussion, for example, through the experience that we have in mining very large streams of data coming out of the Large Hadron Collider, which is our flagship particle accelerator here at CERN. And as we look at these debates, we will be exploring not just the latest developments, what's happening today, but also we will have a view to the future, what's coming down the line. So experts from CERN, but also from other fields, will come together and look from their particular vantage points at what will the world look like, and also what will be the impact on all of us. And this is also why it's not just about the experts, it's also about the public. And the forum has a public event attached to it so that others can engage. Everybody who's interested in AI can engage with the experts and ask questions, spark further reflections on what artificial intelligence means for us as a global society and as a global community.
So, scientific forum, a public event, fall of 21, is it going to be an annual event?
We have planned 3 pilot events within the Sparks concept, and each of them will have a public event attached to it. For the first 2 years, we will be at the Geneva School of Art and Design, which is the top design school here in Geneva. We will be co-hosting the event with them. And then we hope that the 3rd edition can take place at the CERN Science Gateway, which is a new science education and outreach center, which we will be building here on the CERN site and which we hope to inaugurate in 2022.
Charlotte, thank you. I want to see you again at the end of the event in an hour and something. Thank you,
Bruno.
So artificial intelligence is actually evolving at very fast pace. It's actually present in our daily lives, although we may not notice it ourselves. And it has been used and developed here at CERN for many, many years. So let's take a look first at how CERN uses AI. We're going to do that through a video hosted by 2 of the co-curators of Sparks, Alberto Di Meglio from the CERN Open Lab and Maurizio Pierini from the CMS experiment, which is one of the particle detectors attached to the Large Hadron Collider, the largest accelerator on Earth, which sits right here under our feet, 150 meters underground. Let's watch the video.
I think that as of today, we live in the narrow AI era, where we're going from ideas to applications, and this is entering our lives, and this is changing our lives. Strong AI, the general concept of AI, like conscious automata, this is still far away in the future.
The term artificial intelligence and the research on artificial intelligence is not new. Actually dates back to the mid-50s. 56, I believe, was the first conference when this terminology was introduced. One of the most used approaches is machine learning, or one of the flavors of machine learning called the deep learning, that uses algorithms to execute a number of tasks. This particular type of artificial intelligence has been used by the energy physics community for a long time, almost 30 years now.
Since the end of the 80s, particle physicists are using machine learning as a tool to do several computingly heavy tasks. The typical one is tracking particle trajectories when particles emerge from the collision of the beams in the center of the experiments. We collide the beams, particles come out. We don't see the particles coming out, but we see what they leave in our detector. We need to connect these dots, and we use machine learning algorithm a lot to do this since the 80s. And of course, with deep learning emerging in 2012, we moved to deep learning techniques just because they provide better performance.
Deep learning is a specific branch of artificial intelligence and machine learning that uses algorithms, models called neural networks that try to mimic the way our brain works. The networks are given specialized tasks within a full network of algorithms, and each one becomes very efficient, for example, at filtering data, at extracting knowledge, at reducing the noise inside the original data.
Can AI be our mean to do more with less? Physicists are used to emulate with computers the collisions that happen at the LHC in order to understand what they expect to find when they go and do the experiment. And this is done with the algorithms, with the software libraries that were developed at CERN and in the other labs around the world that have encoded all the physics that we know about the interaction of particles with matter. This library is the state-of-the-art of our understanding of how a detector behaves, but it's extremely slow. And so it demands a lot of computational resources, and long-term it might not be sustainable when our amount of data will increase.
In the past 10 years or so, we have seen the availability of new computing platforms or even dedicated hardware for running machine learning or deep learning that has changed the field in many ways. So as a community, high-energy physics community, and specifically at CERN, we are now looking at how to combine these new optimized algorithms, for example, deep learning networks, and this new hardware, not only to do the standard classification tasks that are important enough but are just part of the full chain, but also in applications like simulation, for example, for accelerating, for doing fast simulations, for optimizing the operations of the accelerator, the detectors, or the entire infrastructure, and also for discovering new knowledge. This is a very important part of the new trends in deep learning and artificial intelligence, is really knowledge discovery. This is changing a bit the way we work. Instead of having a model that we want to verify from the data, we can actually ask the data to tell us what the model is. And neural networks are very efficient at doing this.
The big revolution of AI deep learning in the last 10 years allowed us to expand the scope of application from this speed-up tool, let's say, to a different way to look at our data without the inherited prejudice of what the physics we know looks like and what the physics we expect to find should look like. The same way people are training algorithms to generate phases of people that don't exist, we could generate phases of particles that do not exist but represent what the typical particle would do in our detector.
Besides the application of machine learning to scientific data analysis at very large scale, there are other very interesting applications of this technology. For example, the facilities, the accelerator, detectors, or even the computing infrastructure produce themselves a large amount of data. For example, logs from the sensors. Analyzing that information is also very important, especially because as the accelerators become more efficient but also more complex, it is important not to be reactive, solve a problem after it has occurred, but to understand before something becomes a problem how to address it. This is very important because not only allows to keep the facilities in peak performance, but saves quite a lot of money in the process.
At the time of the Higgs discovery, we were using machine learning heavily. Since deep learning emerged, we started the process of transitioning from classic machine learning applications to deep learning applications. And this process is ongoing, and it's already had its first results, but we foresee the biggest impact to come at the next LHC run, and for what will come after the LHC, we expect deep learning to play a major role in the way we do things.
We are also looking at the future. For example, there are interesting combinations of neural networks, artificial intelligence, and quantum computing that could give us even more performance in the future. Another thing, which is a general problem with artificial intelligence is about the ethics of using technology and specifically artificial intelligence in our operations. This is something that is not specifically for physics, but is something that we want to work on together with the community. So in general, besides our specific applications, we are interested in working with the artificial intelligence community and other scientific and industrial experts in understanding the potential and the evolution of artificial intelligence technologies.
So artificial intelligence as a concept was actually born in the 1950s already, with dreams of creating conscious machines. But as Maurizio just said in that video, what could really be understood as machine intelligence is still quite far into the future. However, AI is already providing powerful tools and techniques to cutting-edge research. And to discuss how they're used in high-energy physics, because we are at CERN, I have the pleasure to welcome two of the brilliant minds that make CERN this unique and special place. Particle physicist Jennifer Ngaduba and Michael Kagan. Welcome. Michael, before we take a closer look at how CERN uses AI to analyze data from the Large Hadron Collider, take us through how the data are generated and collected.
Absolutely. So here at CERN, at the Large Hadron Collider, we want to study the fundamental particles, the most elementary particles in the universe, and how they interact. Now, in order to study them, we have to create them, and that takes energy. So that's what the Large Hadron Collider is for. And this happens in 3 steps. First, we accelerate particles. We accelerate protons up to nearly the speed of light. And then in the second step, we collide them. We smash them together to make them interact. And now you may have heard of Einstein's famous equation, E equals mc squared. Well, that tells us that mass is a form of energy. And so by smashing together particles with a lot of energy, we can create heavy particles, the kinds of particles we want to study. Now, those particles don't stick around for long. Many of them decay in less than a billionth of a second. And their debris comes shooting out of the collision. And that's what our detectors are for. That's the third part. We detect the particles that come out of the collision. And with those particles we detect, we can then reconstruct and study what happened in the collisions.
Jennifer, what do you expect to learn from those collision data?
Yes, Bruno, let me try to explain. So by studying the collision data, we expect to complete our understanding of the fundamental laws of nature. So our best knowledge right now is represented by the standard model of particle physics, which describes the fundamental structure of nature, of matter. And it has been built over almost a century of discoveries and theories. And it's a very successful theory. It's actually one of the most successful theories in the history of science. However, there are phenomena that we observe in nature that we cannot explain in this framework. Let's take gravity, for instance. This is one of the 4 fundamental forces in the universe, and it's well described by the Einstein theory of general relativity. However, we do not know yet how to fit this theory in the particle physics framework. Another puzzling phenomenon that we observe concerns the rotation of galaxies, which we see happening at a much higher speed with respect to what we expect by knowing the exact amount of visible matter. So we suspect that there is an unknown form of matter, which we call dark matter, and we do not know what it is. So by studying the collisions, we hope to shed some light on the nature of this new matter. And we can do that in studying the collisions in different ways, depending on which answers we're seeking. So we can either measure with higher and higher precision the phenomena that we already know, or actually search data for something we never observed before, like the production of dark matter particle.
Now, the LHC looks to me like a phenomenal machine, but it's also a phenomenal generator of data in a way. Michael, give us a sense of how much data today and how much data when it's going to be upgraded.
Yeah, so right now the LHC produces collisions about 40 million times a second. And the data that we read out is about a gigabit per second. That's the gigabit per second per experiment. And if you accumulate all that data over the course of a year, so roughly for all the 4 big experiments of the Large Hadron Collider, that's about 200 petabytes. or 200 million gigabytes. So to give you a rough idea, that's something like 200 million movies. That would, if you were watching 10 movies a day, that would take you thousands of years to watch that many movies.
That's quite a lot of data. Jennifer, how do you store this data?
Yeah, indeed, this is a lot of data. And in principle, we could store and process them all, but with the consequence of enormous cost in computing resources. So as physicists, we prefer instead to engineer smart systems that allow us to complete our physics programs while keeping the costs low. And in particular, we start from the fact that not all of those 40 million collisions per second lead to interesting products, like the production of Higgs boson. So we can actually filter the uninteresting ones, and we do this with a system called trigger. You have to keep in mind, though, that the snapshots of the collisions are coming in every 25 nanoseconds, and so we do not have much time to decide if the event is interesting or not. And at that stage, if we don't keep the events, they are lost forever if we don't keep this data. So it has to be made very fast, and the system must be very intelligent, and these are two things that are typically very difficult to achieve at the same time. So we make this working, though, by designing very complicated systems and custom electronics, and at the end, we save only 1,000 of these snapshots per second, starting from the 40 million that we had originally. So at the end, we make physics discoveries with a very little fraction of the original data.
Okay, so Michael, you produce data from the collisions, you filter the ones worth analyzing using algorithms, store them, but store only some of them. What then?
Absolutely. So after these collisions occur, the particles fly into our detectors, and they leave signals. They leave electronic signals that we can read out. And we have to go and take those electronic signals and turn them into an understanding of what happened in the collision. So we take those signals and figure out what kind of particle was there and where it was going, how much energy it had. And that allows us to say, you know, each collision had these different kinds of particles in it. And then we can go and try to find the collisions that had interesting sets of particles. So for example, the Higgs boson, a particle discovered here at CERN, we're very excited to study it. Sometimes the Higgs boson decays into 4 electrons, but that only happens in 1 out of a trillion collisions. So we have to go and sift through all this data and find that 1 out of trillion collisions, and also try to tell it apart from other collisions that might also have 4 electrons. And so there's a lot of algorithms to do that kind of sorting of the data and statistical analysis to estimate the properties of those Higgs bosons.
Jennifer, what's the specific role of AI in this process?
Right. So artificial intelligence, or more specifically deep learning, offer a promising aid in expanding our physics program. In fact, we know now that deep learning methods outperform traditional algorithms in many different physics tasks. And also, we know that with AI, we can let the algorithm learn and teach us the physics rather than embedding our physics knowledge in the algorithm itself. And the former is somehow a faster process. The other big advantage comes from the fact that it's very fast to execute a deep learning algorithm on some specific hardware. And this is an advantage because I mentioned before that the speed is crucial, for instance, in the trigger process, but not only, also beyond that. For instance, to claim a discovery, we compare the data that we collect with our best knowledge. And to do so, we need to create fake data that follow this knowledge. And then we compare with the real data, and if we find a mismatch, we conclude that our best knowledge was wrong or incomplete. And then we hope that the missing part can be filled or explained with maybe a new theory, a new particle, and then someone wins a Nobel Prize. So, however, this process of creating fake data, which we call simulation, is a very computer-intensive workflow. For instance, it can take up to 10 seconds to generate one fake collision and put together all the complex sensor data. While instead we now know that we can speed this down to a few milliseconds with an artificial intelligence algorithm. So this is very interesting because for some of our tasks we can free computing resources and keep the costs low. So in other words, we can do more with less.
When you think of the further development of AI in particle physics, where do you see challenges or stumbling blocks or obstacles?
Right, I think that the main challenge comes from the fact that in the near future we expect the experiments to grow in detector sophistication and in intensity of particle beams. So the consequence then is that the data sets will grow in size and in complexity.
Michael, how does AI learn physics?
It takes data and it tries to find patterns in that data and make predictions about, what might happen or what might be an answer of a question you ask about that data. But it actually doesn't know anything about physics. It's just trying to find patterns. So it doesn't know about the laws of physics that govern the world around us. So for example, if I were to throw a ball and I ask an AI model to tell me where the ball is going to go, it doesn't know anything about Isaac Newton or Newton's laws. It doesn't know the ball shouldn't stop in the middle of the air and turn right around and fly right back at me. So one way to learn, for AI to learn physics is also for us to teach it how to make predictions that are consistent with our laws of physics. And that's an active area of work right now.
Now, let me ask you a layperson question, the question for somebody who doesn't work at CERN. But I'm asking it because you mentioned, both of you mentioned fake data, generating simulations, etc. So under us, there is a big machine, a complex one that cost billions to build, and now it's going to be upgraded in the coming years. Could it just be replaced by a giant AI-driven simulation?
That's a good question. It's interesting. There's a lot of interest in thinking about how AI can help run experiments, how it can help maybe even design components of experiments. But in terms of your question, AI is really good at finding patterns, especially when we give it a little help. But it's not so great at generating ideas, generating hypotheses, answering the question why something happens, and using that answer to why to tell us and inform us what to do next. That being said, in the future, maybe AI will be better at that. And even in that case, even if AI can generate ideas or hypotheses about how the universe works, in the end, there's only one universe. And the only way to know what's happening is for us to go out, build experiments, and make measurements.
So the answer is no in the short term, no in the long term.
Yes, I think so.
Okay, Jennifer, Michael, thank you very much. So that's how data gathering, filtering, analysis is conducted, and how AI is helping particle physicists here at CERN and elsewhere. But what about the hardware? What about the machines where the collisions are generated? The accelerators here at CERN are some of the most complex and largest machines ever built by humans, and AI is increasingly playing a role in running them. So before we explore with our next guest that topic, I want to show you a short video that explains how AI is used in the Large Hadron Collider here at CERN. Let's watch.
The LHC, or Large Hadron Collider, is a particle accelerator. It's actually the biggest particle accelerator in the world. It's a circular accelerator with a circumference of 27 kilometers. And these 27 kilometers are mainly filled by magnets with the purpose to guide particle beams, mainly protons. And the beams are accelerated by the LHC to almost the speed of light. So in the LHC, we have two beams. And the purpose of having two beams is to actually make them collide. And they collide at 4 locations around the LHC ring. And these are the places where we have the big particle detectors.
In order to keep the beams stable inside the accelerator, we need to provide all these magnets with a lot of services like cryogenics, vacuum, electricity, and many other things. So we do this with our control systems that are able to regulate these systems to operate in the nominal conditions, and all this data that is produced is then archived. We try to use AI and machine learning for 2 main reasons in our control systems. One of them is to increase the efficiency by detecting anomalies in the data. And the second purpose will be to try to anticipate what is going to be the evolution of the system, to forecast what is going to be the behavior. And this will help us to understand when the equipment will have to be replaced, but also to tell the operators that they should react because a problem is about to be developed.
To maximize the number of collisions that we have in the LHC, we run essentially continuously for 1 year. And for this, we are running on shift in the CERN Control Center. Our job in the control room is to adjust various parameters, be it magnets, steering magnets, etc., such that we keep, for example, the beam on trajectory, we keep it focused, etc. And for this, we use beam instrumentation. And AI helps us interpreting this beam instrumentation. Now we can actually pick up features that we couldn't do before with classical algorithms. So this is one aspect. The other aspect is that instead of us just taking the readings from the beam instrumentation and then putting this into the control system to set the magnets, we actually let AI algorithms do the entire thing. And this is reinforcement learning. So next to using AI for controlling the beams and controlling the accelerators, we are also working with robots that are repairing machine components during the maintenance periods, and there we're also using AI.
The main function of these robots can be resumed in 3 main functions. The first one is remote teleoperation, the second one is remote inspection, and the third one is quality control. And for all these tasks, the robot uses AI. In case of the remote inspection, AI helps the robot to localize itself within the accelerator. Especially for radiation protection measurement, the robot must be precise.
So what we are working on, in a sense, is to see whether it's possible to, first of all, more automate accelerator operation, to have even, therefore, also more efficient accelerator operation, and then eventually, why not, self-driving accelerators.
If that's not impressive, I don't know what is impressive. I visited once the LHC during one break in the operations, and it looked to me like an underground cathedral devoted to the power of human knowledge and human ingenuity. Now, here is maybe a way to look at AI and particle physics. On one side, scientists operating cutting-edge scientific hardware like the LHC increasingly relying on AI. But on the other side, AI also needing cutting-edge hardware specifically developed for it. My next guest is Sofia Vallecorsa. Welcome, Sofia, an AI and quantum researcher here at CERN Open Lab. Welcome. Tell us how you use AI in your daily work.
Thank you, Bruno. So I use AI to accelerate simulation. Normally, simulation is done using Monte Carlo techniques. This is a generic approach that is used by many different scientific fields beyond physics. And it does a very, very good job at it, in the sense that Monte Carlo results are very accurate. The problem is that it's also extremely demanding in terms of computing resources. So part of my research is trying to understand how to use AI, and in particular deep generative models, to replace Monte Carlo simulation.
So you talk about generative models. Explain maybe that concept to.
So generative models are very interesting models that have become very popular in the past few years. The idea is that they learn hidden distribution from the training data, and then they are capable of reproducing synthetic data that looks realistic, that looks just like the data that they've been trained on. And those are the models that probably you heard of when you read those news about producing faces of fake people.
Deep fake videos, for example.
Or that, or even applications in art. People are starting to use generative models to generate art.
Yeah.
We use them to try and understand if we can replace, up to what level of accuracy we can replace Monte Carlo simulations for our studies.
So let me see whether I understand correctly what happens. So you take what physics already knows. Out of that, you create a computer simulation of how nature, quote unquote, is based on that knowledge. Then you confront it with real world data. If there is a difference between the two, that means that your simulation, your model, is missing something. It's not complete. So that opens up a new space for research, correct?
Yes, that's correct. So it means that we have observed something that we were not expecting, something that we had not forecasted, we were not able to describe. But that is also, but that is just part of the story, in the sense that we can use Monte Carlo also, or simulations in general, also the other way around. We can use it to reproduce a new theory, and then compare this to experimental data, and then validate these new theories or falsify them.
So we started the discussion talking about hardware. So how the machines, how does it work in practice?
One of the reasons why deep learning has reached such a high level of, has reached such good results recently is really the availability of a lot of data that those models can be trained on, but also the availability of new and very powerful hardware. So
I mentioned at the beginning, introducing you, that you are a quantum scientist, and that's a field that's obscure to most people. But in recent times, you've read a lot about it. You've read about Google achieving quantum supremacy, the European Union launching a flagship research program funded with billions of euros. So how is quantum gonna help this quest?
So there is indeed a lot of enthusiasm around quantum technologies in general and quantum computing in particular. I think the reason is that we are getting closer to the moment in which quantum computing will be able to solve practical problems. And yes, you mentioned Google's announcement on quantum supremacy as one of the examples, but in general, it's probably not something that will happen right away, but we need to get ready for it. We need to understand how to best use them and how to best integrate them in our scientific research.
So far we have talked mostly about how CERN uses artificial intelligence to optimize data gathering, data analysis, and the operations of their complex machines. This, however, is the launch of the Sparks initiative, which from CERN wants to investigate the future of AI. So Sparks has an editorial board, and the board has identified 7 key topics that will be discussed as part of these initiatives, and which are central to figuring out the kind of impact that AI may have in the future. The first question, of course, is how do we move from pattern recognition, which is essentially what AI is doing in different ways today, towards strong AI? And as we do that, we are going to come up against limitations in current hardware, for instance. What are the missing building blocks? And we will feel the limitations of the underlying models. That will raise even other questions of ethics and fairness. Who makes the rules? How do we avoid bias? Who has the power to decide what? Is AI good or evil? That will then lead to the question of whether and how AI will close in on human intelligence. What contribution can AI give to society? And because we are at CERN, what contribution can it give to fundamental research in physics, cosmology, genetics, and other fields? And then finally, that special question of creativity and curiosity, the ultimate human characteristics. Can AI learn to think out of the box, out of the data set, let's say? Can AI be a creative force? Will the future artistic masterpieces be created by machines? Those are the 7 areas that Sparks is going to discuss and investigate in 2021 and beyond. And to start, we're going to talk about some of the current breakthroughs in AI with our next guest. So far we have understood a bit better what AI is, how it works, how it is used here at CERN. And we have asked a series of questions about the future of artificial intelligence. Let's look a bit into that future. What is the path towards strong AI? And what breakthroughs can be expected in the shorter and in the longer term. As I mentioned earlier, this is the launch of the Sparks initiative. The main event is going to take place next year. There's going to be a scientific part and a public part. And one of the confirmed participants is Anima Anand Kumar. She joins now from Los Angeles, California, where she's the Brand Professor of Computing and Mathematical Science at Caltech, and she's also Director of Machine Learning at NVIDIA. Anima, welcome. Thank you for being with us.
Thank you, and thank you.
You are an expert in machine learning. You have been involved in developing both the algorithms and the computer capabilities. We have agreed that you will start with a short presentation, and then we will have a discussion. So I'm going to give you the floor. Tell us, what is the status of AI today? Where is AI research today? On to you.
Today, I'd like to give a brief overview of the path towards generalizable AI. Over the past decade, deep learning has seen such tremendous developments. And I'd like to call this the trinity of AI, because the deep learning algorithms are just one facet of this trinity. The other two important facets are data, and it started with the collection of ImageNet dataset at scale and the compute infrastructure, especially from NVIDIA GPUs. So the three of this coming together, data, algorithms, and compute, has created this deep learning revolution. And for us to take this path forward, we need to ask how to innovate on all these three fronts. And indeed, we've seen such impressive growth. You can think of many important developments over the past decade. For instance, the deep reinforcement learning beating the human champion in Go, or the NVIDIA GANs generating such photorealistic images of human beings that you cannot tell that they're not real people. And so these are aspects that we hadn't imagined a decade ago. Yet, there are so many gaps in our current AI systems, and many applications haven't lived up to their hype. For instance, autonomous driving has been in the news so much, but we still don't see fully self-driving cars on our streets. And that's because these are safety-critical applications where you have even a minor change in the environment could sometimes lead to failure modes of AI. And there's so many scenarios that can happen in the real world. Another important drawback is the lack of understanding, especially language understanding. And what we've seen during this pandemic is the attempt to replace human content checkers with AI and not being successful there. So humans are still needed to ultimately moderate content in so many scenarios. So these are some big gaps. And the question is, how do we fix these gaps? How do we go to the foundations of deep learning algorithms and then innovate there? And to do this, I'd like to think of breaking down any AI algorithm into three parts. First, the question is, what kind of data does it require? Does it expect labeled data, or can it also work with unlabeled data? What is the quality of data that it expects? The other is the prior knowledge. What knowledge do we know about the domain? For instance, if we are working on images, we usually use convolutional neural networks because convolution is a prior knowledge in terms of having translation invariance in our features. And the other aspect of an AI algorithm is decision making. So what kind of task should this method be trained for? Should it optimize for the overall accuracy? Should it optimize for accuracy for each category? Right? These are some specifications we need. And then it also needs to take actions. For instance, if it's a deep reinforcement learning method, playing the Go game, it needs to go and make the Go move. And so these are natural ways to break down what an AI algorithm does. It learns from data. It takes in some prior knowledge. It has a task specification, and then it takes actions. And with the current deep learning methods, the data requirements are massive. And usually it's labeled data. So that's requiring now expensive human labeling. The priors are quite weak. In fact, you can easily fool the current AI systems. For instance, there have been many studies shown where if you put imperceptible noise in your image or simple blocks in the image, it can completely change the end result for an AI system. And hence, we need to think about better priors that are more robust and can help us get it closer to the robustness of human perception. Finally, the task specification is very simple. The most common scenario is we specify a single task for the AI to solve, and the benchmarks are fixed and limited. So this is not only limiting in terms of its capabilities, it can also be dangerous. There have been now many studies showing that there is deep bias in these AI systems that can cause societal harm, especially to minorities. We've seen that in our face recognition benchmarks. So it's important to also think about the societal implications of collecting imbalanced data, having weak priors, which lead to brittleness, and having simplistic task design. So how do we go out of this to the next generation AI methods? And the agenda that I propose is to have data that is unsupervised, or rather unlabeled. We need to do more unsupervised learning. Infants predominantly do unsupervised learning. They're observing the world around them, and only after they develop language and speech are they able to get the supervision of what's each object that they are seeing. We need to build such scenarios also for AI. The other aspect is priors. How do we build more robust priors? Incorporate domain knowledge. For instance, if we are solving for quantum chemistry, we need to think about the known structure of how atoms are organized in molecules. So it really depends on the domain, what kind of prior we need to design. Also, there are some general priors, like taking inspiration in terms of how our own brain is so robust and how it has feedback and can hallucinate and we can dream. So these are aspects we can build into all artificial networks, and we've done that. And the last aspect of task design is also so important. How do we move away from a single task to many different tasks, be able to span multiple domains, especially in domains like robotics? We have a lot more data in simulations. If we can create high fidelity, physically valid simulations, then can we take the AI system from simulation to reality? How do we close that domain gap? And how do we ultimately build systems that are lifelong learners, that can learn and keep learning? And to me, these aspects of doing unsupervised learning, building robust priors, having adaptive task design is a key set of ingredients to create a next frontier in AI. Thank you.
Anima, thank you. I want to go slightly deeper into some of the points you made. And the first one is about supervised versus unsupervised learning. You mentioned labeled data and unlabeled data. So right now, the dominant paradigm is supervised learning. So AI systems learn out of data sets that are labeled and characterized by humans in different ways. There is this new space called unsupervised learning, where essentially the machine is learning about some parts of the world, about from other parts of the world. How does that actually work? Give us a sense of how that can happen when a machine that's blank is exposed to the world.
Yeah, that's a great question, Bruno. And to me, I take a lot of inspiration from how we learn, right? Infants are just observing the world. They don't have speech and language capabilities and they're understanding that there are patterns. They start to recognize their mother and their, father and close family members. So it's like proceeding, as you can see, in stages, right? And we haven't yet created such AI systems. But there's lots of very useful and pertinent applications that can use unsupervised learning. And some of them don't even require deep learning, right? So I was working on algorithms for document categorization before deep learning came along. And there, if you think about a very large set of documents, maybe all articles of news over the past decades, that's humongous. You cannot get humans to go label what are the topics in each document. And there are also many, many different topics, right? It's not just a single topic in a document or an article. And so how do we now let the algorithm tease out what are the topics and come up with a categorization, right? And then, of course, it's up to the human to interpret that, okay, it's saying that these documents are sharing a common topic, maybe that's the topic, right? So it still requires human to ultimately go label and interpret the topics. But then the algorithm can automatically come up with this categorization.
Yeah. Another point you mentioned is the question of adaptivity, right? If we train a machine to do X and it can't do Y by itself, it needs to be retrained to do Y. And that's also roughly, not always the case, but roughly where we are today. How do we break out of that limitation?
Yeah, that's a great point, Bruno. And I think it, of course, depends on the application. I think the most common ones involve robotics, right? So a robot that is interacting with the environment can come up with so many different scenarios. We have a paper that's appearing in the conference of the Robot Learning Conference next year, where we show that designing it in simulation, you can let it now have a curriculum. So this four-legged robot can first learn to walk slowly, then quickly on a treadmill, then it can come up with more complicated moves. It can start climbing. So you can give it a whole curriculum of tasks in simulation. And then bringing that to the real world, you need robustness. And what we've done is hierarchical reinforcement learning. So meaning the low-level controllers, you're not learning from scratch, right? And there's no need to, because control theory has given us there are for control people who've designed such robust controllers. So if the controllers can do primitives like walk, trot, or stand, what the learner is doing is learning how to mix it up to adapt to different surfaces. So even if it comes across a frictionless surface or a low friction surface, a slippery one, it can still stand, whereas a system without adaptivity would slide out.
So you work at the interface of business and academia, right? I mean, you work on both sides of the equation. Where do you think the next big breakthrough is going to come from?
Yeah, I mean, I'm so privileged to be both at NVIDIA and Caltech, and bridging the gap between industry and academia gives us so many new opportunities. And I think, to me, the next breakthroughs will come from such collaborations. One example is the project that we are doing to replace traditional methods to compute quantum energy calculations. These are hugely expensive calculations with deep learning. So it needs domain expertise. I'm working with Tom Miller at Caltech, collaborating with him, his professor in chemistry, with deep domain knowledge. And also now scaling it up in collaboration with NVIDIA to really large supercomputing scale. And so as you can see, it requires deep collaborations and deep knowledge. But ultimately bringing this together can unlock so many new things. For instance, drug discovery is very much having the energy calculations as its foundation, discovering new materials, new catalysts for renewable energy. All this has that as the foundation. So to me, taking the foundation from the sciences, right, and then accelerating that with AI and deep learning, and hence enabling new scientific discoveries, that's what is my passion. Indeed, I talked to Mario Spiropolo at Caltech, who used to be at CERN for a long time, and I'm trying to understand the domain, right? There is, I think, disruptions needed at different aspects of it. One is, taking the traditional pipelines, right, of how the experiments are planned, how the data is collected, how so much of data still cannot be collected because there is just such a wealth of data in those explosions when they happen. So how do we, kind of make better sense of what to collect, how to design experiments, and how to do the post-analysis, and ultimately make this available to a broader scientific community, right? So that people can see how different algorithms are working, they can share more easily, they can reproduce better. I think all aspects of this will see better evolution, and I think that's really exciting to be a scientist in this decade.
So to end, let me ask you a couple of questions about another topic I know is close to your heart, which is diversity. I've seen you quoted saying, diversity is the mother of creativity. Can you elaborate?
Absolutely. To me, there is now so much increasing awareness on the role of diversity and inclusion in all organizations. And to me, to design new AI, it's so important to have a diverse team. Because, for instance, I mentioned AI bias, and I mentioned face recognition being one of the most applications that's in public's mind. And that's because thanks to Black female researchers, Joy Bolam-Winnie and Deb Raji, that first showing this in their gender shade studies, running up against big companies, having the bravery to do that. And I always think if the teams themselves are much more diverse, maybe that would have happened much earlier, right? So it's so important that we are building now AI for people, that incorporates people's data, that serves people, whether it's like voice recognition systems, whether it's face recognition, personalization. And so we need to make sure we have a diverse team to build the best systems for everyone.
So one way of saying that, and I think that you said that because I've seen that somewhere written, is that diverse teams make biases come to light. And that's very relevant in AI research, of course. I hope I quoted you correctly.
Absolutely. And it's so important to do that early on, right? Rather than release everything out into the public, because now these scientific progress is moving fast. AI progress is happening so fast. And we still haven't thought about all the societal effects. We are launching them before we can figure that out. There is no regulation. There is no public policy yet. So I think a lot of responsibility rests with the AI scientists, with AI engineers, and with the companies. So we need to be mindful of that. And that's where I believe that diverse teams can lead us ultimately to having AI for the benefit of society.
So just to close, and forgive me the question, but diversity can help build a better AI. Can AI help promote diversity and inclusion?
I believe so, if it is designed well, right? So AI now is getting more democratized. We see so much of online resources available. This is an open source revolution, right? Unlike the previous scientific progress that was still locked up in journals that were behind a paywall, or lots of compute being not available. We now have cloud providers, we have open source code, we have so much educational materials available. And I hope that this can lead to even a richer ecosystem and more openness.
Fantastic. Anima, thank you very much for taking the time, for being with us today, and I look forward to seeing you next year in Geneva. Thank you.
I do as well. Thanks so much.
Thank you. Now, remember those 7 topics that I described earlier? Well, some of them covered issues such as data privacy, algorithm transparency, ethics, philosophy. Our next guest has that very word, ethics, in her official title. Francesca Rossi is the AI ethics global leader at IBM. She's also one of the confirmed participants at Sparks in September 21 here in Geneva. We recorded a short talk with her just a few days ago about the ethical questions surrounding AI today and how to address them. Let's watch Francesca Rossi.
In the future, humans and machines will increasingly work together as a team. To build effective teams, it is essential to build an ecosystem of trust. AI ethics identifies, studies, and proposes solutions to ethical and trust issues related to artificial intelligence. AI is a science and a technology that has applications in almost every area of our everyday life. We use it when we use a credit card, when we search something on the web, when we use our camera to take a picture, when we give vocal commands to our phone or another device, and when we use many of the apps and social media platforms. Companies of every size and business model all over the world are adopting AI solutions to optimize their operations, create new services and work modalities, and help their professionals in making more informed and better decisions. The use of AI is so pervasive that naturally it raises questions and concerns. First, AI needs a lot of data, so questions about data privacy, storage, sharing, and governance are central for this technology. Also, often the most successful AI techniques, such as those based on machine learning, are opaque in terms of allowing humans to understand how they reach their conclusions from the input data. This does not help when trying to build a system of trust between humans and machines, so it is important to adequately address concerns related to transparency and explainability. Machine learning is based on statistics, so it always has a percentage of error, even if very small. This happens even if no programmer actually made any mistake in developing the AI system. This raises questions and challenges related to responsibility and accountability. Based on the huge amounts of data that surrounds every human activity, AI is able to derive the insights and knowledge on which to make decisions or recommend decisions made by the human being. However, we need to make sure that the AI system understands and follows the relevant human values in the context in which such decisions are made. A very important human value, for example, is fairness. We don't want the AI systems to make or recommend decisions that could create discriminations among groups of people. How do we make sure that AI can act according to the most appropriate notion of fairness or any other human value in each scenario in which it is applied? As I mentioned earlier, AI is very pervasive and its applicability expands very rapidly, so a negative impact of this technology may be very bad for individuals and society, so it must be avoided. Also, it has an impact on jobs, since it can perform some cognitive tasks that usually were done by human beings. And this impact needs to be well understood and addressed. The pace at which AI is being applied also brings concerns about people and institutions having enough time to understand the real consequences of its use and avoid a possible negative impact. Although AI has a lot of applications, it is still very far from achieving forms of intelligence close to humans or even to animals. However, the fact that this technology is mostly unknown to the general public raises concerns about being able to control it should it achieve a higher form of intelligence. AI ethics is a multidisciplinary and multi-stakeholder field of study whose goal is to understand how to optimize AI's beneficial impact while reducing risks and adverse outcomes. For AI developers, AI ethics helps them design and build AI systems that are aware of the values and principles to be followed in the deployment scenarios. More generally, AI ethics identifies, studies, and proposes technical and non-technical solutions for ethics issues arising from the pervasive use of AI in life and society. AI systems usually do not work in isolation, but rather help other human beings to make better decisions. Examples of domains where this happens already is healthcare, financial services, the public sectors, and also the judicial system. It is therefore defining a form of augmented intelligence, where the intelligence here is human's intelligence, rather than creating a new form of artificial intelligence. Consider, for example, a doctor and an AI system that helps him identifying the best therapy for a patient by analyzing huge amounts of data, or even a scientist who can use AI to identify the most promising hypotheses to be then carefully considered with standard scientific methods and experiments. In this context, it is essential that the AI system knows how to effectively work with a human being and how to follow the guidelines and principles required for the decision scenarios. On the other hand, also the human being must understand how to work with the usually statistic-based machine and how to integrate what the machine is providing in his or her decision-making process. In other words, the human and the machine must form an effective team. To do this, as with any team, trust is essential, and this needs to be based on transparency and explainability. This is why such AI properties are so important in order to get all the benefits of AI and avoid the possible negative outcomes. Machines can even be instrumental in helping humans with their own limitations and biases, by alerting them when they see behaviors that are not aligned to the stated principles. But to do this, AI needs to be aware of such principles. No single company can solve all these issues alone. This is why AI ethics include experts of many sciences and technologies. The AI ethics community includes AI experts, of course, but also philosophers, sociologists, psychologists, lawyers, policymakers, civil society organizations, and many others. Only by including all the voices, such as those that produce AI, those that use AI, those that regulate AI, those that are impacted by AI's decisions, those that understand how to evaluate the impact of a technology on people and society. So only by including all these voices, we can understand how to identify and address the AI ethics concerns. Technical solutions to AI concerns, such as software tools and algorithms to detect and mitigate bias or to embed explainability into an AI system, are certainly necessary, but they are not enough. Also, non-technical solutions such as guidelines, principles, best practices, educational and reskilling activities, standard audits, and also regulations needs to be considered. On top of this, there is the need for specific methodologies to operationalize AI ethics principles. For example, in IBM, we have started with few very high-level principles. We then identified the main pillars of trustworthy AI: fairness, transparency, robustness, explainability, privacy, and then we defined the governance frameworks led by the internal AI ethics board to enforce the guidelines and help developers adopt the new methodologies. Each company should devote time and resources to understand the most appropriate way to operationalize AI ethics principles for their business model and their application scenarios. Current AI has still many limitations. It needs a lot of data to learn how to solve a new problem. It cannot understand causality very well, thus has a limited form of explainability. It does not have common sense reasoning, therefore goals have to be specified completely and correctly. It is very good for solving a single problem, even better than humans. This is the so-called narrow or weak AI, but cannot learn from one problem to solve another one. This would be the so-called broad or general AI. Humans, on the other hand, have many capabilities that AI does not yet have. We can adapt rapidly to new environments, we can reason at various levels of abstraction, we can learn from one problem how to solve a different but related problem. What gives us these capabilities, and how can we inject them into AI systems? My current research project proposes to overcome current AI limitations by taking inspirations from cognitive theories of human decision-making, such as the System 1 and System 2 or Thinking Fast and Slow theory developed by Nobel laureate Daniel Kahneman. Daniel argues that there are mainly two broad modalities, two systems in our decision-making process. The first one, System 1, is based on intuition, and the second one, System 2, is based on more careful and conscious reasoning. thinking. We use system one, the thinking fast, most of the time to make quick and almost unconscious decisions, such as recognizing friends in a crowd. We use the second one, the system two, the so-called thinking slow, more consciously for complex decisions that have long-term consequences, such as job hunting or buying a house. The idea of the project is to create a mapping between how people make decisions with these two modalities and how they switch between these two modalities, and how machines could embed such behavior. The goal of the project is to define a theory for a more advanced form of AI that can be more effective in helping humans achieve their most important goals. AI is a powerful technology with a huge positive impact on our lives. At the same time, the transformation it brings to our personal and professional life are significant and fast. And this raises some concerns that needs to be addressed. AI system needs to be designed to be aware of and to follow important human values so that this technology can help us make better decisions which are also wiser and value aligned. Only a multidisciplinary and multi-stakeholder AI ethics approach can satisfactorily address issues such as privacy, transparency, accountability, and fairness in AI, and can help define AI governance frameworks that are effective, enforceable, sustainable, and beneficial. In this way, we can make sure that AI is really beneficial for all and supports human goals and well-being.
Thank you, Francesca. Now, another speaker who's confirmed for next year's forum is Stuart Russell, professor at Berkeley University. Stuart is joining us now via video conference from California. Welcome, Stuart. How are you?
Thank you, Bruno. It's great to be here. I'm sorry I can't be there in person.
Well, that's going to be for next year. Stuart, part of your work focuses on decision-making on AI, in AI, and recently, you have emphasized the importance of steering away from developing AI for single objectives and taking into account the context in which AI is actually implemented and embedded. We have agreed that you will start with a short talk about the roadmap towards strong AI, how we go from here to there, what we need to pay attention to along the way, and then I'm going to come back and I will have a few questions. So the floor is yours.
All right, thank you, Bruno. So first of all, let me say what strong AI means. Sometimes called artificial general intelligence or human-level artificial intelligence. So it means AI that can solve pretty much any task that you could give to any human or any group of humans to solve, and it would do at least as good a job, maybe better. And this means in the real world. It doesn't just mean in virtual reality or on a chessboard. It means in the real world that we live in and function in. So first of all, let me say, it's not about to happen. It's not imminent. We're not going to wake up tomorrow morning and find that the world's been taken over. And second of all, you asked for a roadmap, but a roadmap suggests that once you have a roadmap, you simply go along the road and you get there. But if along the road there's a step that says, and then a miracle happens, right? We don't call that a roadmap, right? And I think really several miracles, several conceptual breakthroughs have to happen between here and strong AI, and that's really important to understand. And unfortunately, unlike advances in hardware, memory size, processor speed, and data resources, unlike those, with breakthroughs, we can't predict when they're going to happen. So people always ask me, okay, when are we going to have human-level AI? And I say, I don't know. And also, it's very dangerous to make those predictions because they always turn out to be wrong. And just to give you an illustration of that, since this is CERN, if you look back at the history of nuclear physics, right, in the early years of the last century, we knew that nuclear energy existed. We had special relativity. We knew the mass defects between different atoms. We knew how much energy was stored and potentially could be released if we could make transmutations of atoms. But Rutherford, who was the leading nuclear physicist of that era, was absolutely adamant that it was impossible. And he gave a speech on the 11th of September 1933, where he was asked that question: would it be possible, maybe in 20, 30 years, that we could ever release the energy of the atom? And he said, no, it's impossible. And then the next morning, Leo Szilard invented the neutron-induced nuclear chain reaction. So it went from completely impossible to basically solved in 16 hours. So that's what I mean by unpredictable. Fortunately, with AI, there's more than one breakthrough that we need. So, even if you think of this as a Poisson process, as the statisticians call it, it's still probably going to take a while. So what's missing? As I see it, there are roughly three major areas where we don't know how to make progress. The first one might seem very simple: systems that know things. And in fact, in the early days of AI, this was how systems were built, using the technology of mathematical logic. And we did have systems that knew things, that could reason with them, but they couldn't scale up and they couldn't handle the complexity and imprecision of the real world. And the reason why you want to know things is, first of all, so that you can do things like physics, right? It's hard to imagine building a radio telescope or a gravitational wave detector if you didn't know any physics at all, right? And we're not expecting that termites are going to start building radio telescopes anytime soon. So that's good. So we use knowledge to know things, but we also use knowledge to learn, right? We can understand what the gravitational wave detector is telling us. It allows us to learn something about the universe and about physics because we know a lot already. And this is probably the biggest difference between deep learning systems, which are all the rage these days, but we don't have any way of putting knowledge into them. So they're always addressing every problem from scratch, which means they require massive quantities of data to learn anything, far more than humans need to learn the same thing. The second big open problem is language, because language is how we acquire all of that knowledge. And so systems that could really understand language, that could actually extract the underlying knowledge content of books and journal papers and so on, that would be an incredibly powerful tool, because a system like that, unlike a human, a system like that would be able to read everything the human race has written and understand it and integrate all that information before lunch. The third big thing is the fact that we are able to operate successfully over long timescales. So let me expand a little bit what I mean by that. If you look at AlphaGo, right, which is the Go program that beat the world champion, AlphaGo seems to look ahead extremely well. It seems to operate over even longer timescales than humans can. It looks ahead 50, 60, 80 moves into the future. And humans don't have the short-term memory capacity to do that. Okay, so why couldn't you just take that algorithm and apply it to the real world? Well, what is a move in the real world? Well, if you're a robot or a human being, a move is sending an actuation signal to one of your muscles, right? And you can do that about once a millisecond. So if you look ahead 50 or 60 moves in the real world, that gets you less than 1/10 of a second into the future, which is completely useless, right? And we operate on timescales of minutes, hours, days, weeks, years. If you decide to do a PhD, that's about 1 trillion motor control actions. Right? Now, you're not planning them all out in detail, but nonetheless, we can make decisions on all of these different timescales and operate seamlessly at every timescale simultaneously. And also, well, how do we do that? We do that because we have all these different levels of abstraction. You have the ability to type a single letter on your cell phone, but you can also think of it as, typing a word. You can also think of it as, text my son and ask him to bring some milk from the store, right? That's an action. You could have another action like do the shopping, right? Another action like, get ready to go away for the weekend. and all the way up to multi-year actions. And this is what enables us to function successfully in the real world. And right now, we don't know how to get AI systems to operate that way. And in particular, we don't know how to get them to create all those levels of abstraction that allow us to function successfully. So those are the three big open questions, I would say, that we don't know how to solve. But any one of those would lead to massive advances in the practical capabilities of AI systems.
So you are on record saying that the biggest limitation is our ingenuity and then physics, right? Which one we're going to break through first, do you think?
So let me start with physics. Some people have argued that physics, the limitations of on computing that physics imposes would prevent us from achieving human-level AI. So I find this very, very unconvincing. So first of all, our brains operate on physics, and they're clear existence proof that physics doesn't prevent human-level AI. Secondly, if you actually look at the physics, it seems that in a brain-sized object, you could do about 10 to the 35 more computation than the brain does. So we are 35 orders of magnitude away from hitting the real limits of physics. So in Max Tegmark's book, Life 3.0, he goes through this in some detail based on some calculations that other physicists have done. And so I don't think we have to worry that physics is going to prevent real artificial superintelligence. Ingenuity, I think, is the issue, right? There's these three, and maybe if we solve these three problems, there'll be more that we haven't thought of. They require someone brilliant to come along and have an insight like Leo Szilard did with nuclear physics to unlock those problems.
So let me pick up on a couple of other things you said. You used the word miracle, and you used it to describe kind of unpredictable events, right? Suddenly there is a leap and we didn't know where it comes from, or we didn't expect it, or we consider it impossible. But there is another kind of miracle that we see more and more when we talk about AI, and it is the notion of the black box, right? Do we even know why these machines work? The machine figures out that this is a cat and that's a dog, but we don't actually know why the machine gets to the result. I'm simplifying here, of course. But how far can we go keeping the logic of the black box central to the development?
In my view, it's just not a viable strategy. And there are several technical reasons for that I won't go into. But basically, intelligence is a complicated thing. The idea of the black box is that you put enough stuff into the black box, and then you have one organizing principle, which is to make the black box do a better job. And essentially, you jiggle what's inside the black box, and you keep jiggling and jiggling and jiggling and jiggling. Every time it does a better job, you jiggle it more in that direction. And that's it, right? So there's one principle, basically, of essentially randomly mutating what's inside the black box to try to get it to move in the right direction. And I just don't believe that one principle is enough to create human-level intelligence. And there are many other principles that we've already learned, actually over thousands of years. So going back to Aristotle, concepts of knowledge, elements of knowledge with precise mathematical semantics that can be combined according to fixed rules that are guaranteed to preserve logical truth. That concept is extremely important and is totally absent from the black box method. The idea that you can make decisions by projecting possible actions into the future and finding action sequences that lead to good outcomes, that idea is also thousands of years old, and yet it's completely absent from the black box approach. So it seems ridiculous to throw away miraculous conceptual breakthroughs that we've accumulated over thousands of years and just replace them all with this sort of one principle of jiggling the contents of the box until it gets better. And actually, we tried that. Back in the 1950s, there was this idea of program evolution, or what we more recently call genetic programming. The idea that you could take programs and do to them what evolution does to genomes, which is to do random mutations and then random combinations or pairs of genomes. So pairs of programs get mushed together to make new programs. So program evolution, people correctly said that in principle, if I keep doing this, I will create general purpose intelligent machines. But of course, in practice, that might take 10 to the 1 billion years. So, gazillions of times longer than the lifetime of the universe to ever produce anything useful. And people tried doing this with Fortran programs because that was the only programming language available. And it was a complete and utter failure. I think we've been amazingly lucky that the current black box methods are really surprisingly successful. But as you say, we don't know how they do it. And that's not a good basis for engineering progress.
Yeah. Algorithms can be both good and creepy, right? Depending on the context and depending on the application and where we put them to work. You're on the record saying that developing strong AI would be the biggest event in human history, but we need to make sure it's not the last event in human history. Can you elaborate?
Sure. So the biggest event in human history, because human civilization is the result of our intelligence. And this would be the first time that we have access to much, much more intelligence than we have inside our brains. So it's inevitable that it would change civilization forever. And quite possibly some of the other candidates for biggest event, like, developing faster than light travel or figuring out how to live forever, right? Those things are much more likely to happen if we have access to super intelligent AI. So the upside is really enormous. The downside, the reason why it might be the last event, is something that actually Alan Turing said. So Alan Turing is the founder of computer science and of AI as well in many ways. And he said that we should have to expect the machines to take control. That once he said, once the machine thinking method had started, it would not take long to outstrip our feeble powers. And it's just common sense, right? Intelligence is what gives us power over everything else. And now we're expecting to make something that's more intelligent than us, and yet we're going to have power over it
Feel that we can
forever.
control it, exactly, yeah.
Right? How? So once you lose control to something that's much more intelligent than you don't get it back. So the question is, can we square this circle, so to speak, right? Can we produce something that's more powerful than us and yet have power over it forever? That's what I'm working on.
So many people would answer that by saying we need to build human values into the machines. How do we do that?
So building human values into the machines is a statement that sets off a lot of warning flags, especially these days. So whose values? How do you do it? What if you get it wrong? The problem that we have with AI right now, and the reason we would lose control, is that the standard model. So I'll use the phrase standard model because we use that in physics. Right? The standard model of AI is to build optimizing machinery and then put in the objective for the machine to optimize, and off it goes. So you build a game playing program, you put in the objective of winning the game of Go, winning the game of chess, and off it goes. And that standard model is pretty pervasive. It's not just AI, it's control theory, it's statistics, it's economics, and it's a mistake. It's a mistake because if you put the wrong objective into a machine that's more intelligent than you, then basically you've set up a chess match between us and the machine where the stakes are control over the world. And we lose that.
Yep.
So So the whole model is wrong, and we're already starting to see this, right? It didn't matter when the AI system was a toy and it was in the lab, and the worst thing it could do would be to beat you at chess, right? But as we move them into the real world, right, you look at the learning algorithms in social media, they are laying waste to our civilization. Why? Well, because they're defined with the wrong objective. And that objective leads the algorithms to manipulate humans in ways that have actually been deleterious to us, because the algorithm, that's not its objective. Its objective is to get you to click on things. It doesn't care what effect that has on civilization. We forgot to put civilization into the objective. So you get these really negative outcomes. And the solution is actually to get rid of the standard model altogether, to get rid of this idea that we have to specify the objective, because we can't. Right? And we've known this for thousands of years. Every time you get given 3 wishes by a genie, right, what's your 3rd wish? Please undo the first 2 wishes because I screwed it up. Right? So we can't do it, and we know we can't do it, so we shouldn't assume, we shouldn't base our engineering methodology on a false assumption that we can specify objectives correctly.
Yeah.
So what we should do is build machines that know that they don't know what the objective is. Right?
Stuart,
and that humility is what turns out to give us control.
Stuart, just to close, a question that is unrelated to this, but not completely. We live in strange times. The year has been dominated by the COVID-19 pandemic all over the world. You are not here on this stage, but you are via video conference because of that.
Yep.
What role is AI playing in our fight against the virus, and do you think we are using it to its full extent at this point?
So that's a great question. Let me first say, AI is not a panacea. Many people ask, well, why doesn't AI just solve the pandemic if it's so clever? It's just not in that business, right? The solutions to the pandemic are social solutions and medical solutions. And AI, at best, we don't have super intelligent AI. It cannot invent a cure for the virus. At best, it could have provided us with a much better early warning system. So integrating data from many different sources to detect and characterize the very early stages of a potential pandemic. It can probably improve on the mathematical models that people are currently using, partly because it's able to integrate data at every level of abstraction. So we can, not using black box method, but actually using methods based on what we call probabilistic programming, where we can actually construct models that go all the way from the individual person moving and acting and infecting other people, all the way up to aggregate level data at the level of a state or a country, and can learn those models from collecting data at all levels of detail. So we could do a better job of pandemic modeling, and then that gives you the ability to do a better job of intervention and prediction. But all of that takes a lot of time.
Yep.
And arguably, yeah, we should have started 10 years ago, and it's a bit late now, and it's probably not going to have a real impact before the vaccine arrives.
Well, maybe we can start now to prevent the next one. Stuart, great having you with us. Thank you. I look forward to seeing you next year here on this stage. Thank you for taking the time. Enjoy the rest of the day.
Me too. Thanks very much, Bruno.
Thank you.
Bye-bye.
Now, Stuart just mentioned the importance of taking into consideration in the development of AI the context in which it ultimately acts and operates. Many organizations focusing on AI research are struggling to connect the technology development with the human aspects, human values, ethics, philosophy, creativity, and other similar questions. And actually, the field is pretty divided on these topics. Now, the final contribution of today comes from a true AI pioneer. If you use an iPhone, you're actually carrying in your pocket some of the technology he and his team have developed. Several years ago, he outlined in a paper a vision on how AI could achieve creativity and even curiosity, which are essential, quintessential human characteristics. So we invited him to explain what that would mean. From Lugano in southern Switzerland, where he's working on building the first practical general-purpose AI, it's a pleasure to welcome Professor Jürgen Schmidhuber.
What is creativity? In my point of view, there are two types of creativity, applied and pure. Applied creativity is this: some external source poses a problem and some problem solver tries to solve it by creatively generating all kinds of solution candidates until the problem is solved. Humans and machines have been doing this for a long time, for example in chess or in Go or in many other applications. Pure creativity is when the problem solver does not slavishly try to solve problems posed by others, but also invents its own problems. That's what babies do when they play with their toys. They invent their own questions. What will happen if I do this? Science is about asking questions, not only answering questions, but also asking questions. And the baby asks, what will happen if I do this? If I let this toy fall to the ground? And that's also what scientists do when they set up their experiments to figure out how the world works. They are trying to answer self-posed questions. And this also applies to artists and musicians. For 3 decades, we have built machines that invent and solve their own self-posed problems, that invent their own questions and try to answer them. Once the answer is known, the subject becomes boring, and the machine tries to invent a new question whose answer is not yet known. And over time it learns to ask better questions and find better answers. Many humans feel that certain machines already have a strong form of applied creativity. For example, Go players coming up with creative winning moves that no human ever thought of. And some people also perceive creativity in artificial neural networks that have learned to draw novel drawings in the style of certain famous artists. In 1990, I introduced a new type of active, unsupervised or self-supervised learning with intrinsic motivation. It is based on a minimax game where one neural network tries to minimize the objective function maximized by the other neural network. Today I refer to this duel between two unsupervised adversarial neural networks as adversarial artificial curiosity. So how does adversarial artificial curiosity work? There is a controller neural network which probabilistically generates output actions that may influence an environment. And there is the world model neural network that learns to predict the environmental reactions to the outputs of the controller. So it learns to predict the consequences of the actions of the controller. The world model learns to minimize its error, so the deviations between what it predicts and what really happens, and in this way it is becoming a better predictor. But in a zero-sum game, the controller tries to find output actions that maximize the error of the world model, whose loss is the gain of the controller. Hence, the controller is motivated to invent novel outputs or experiments, action sequences that yield data from the environment that the world model still finds surprising, until the data becomes known and boring. Yes, they keep fighting, and in the process both of them get smarter. So the world model neural network learns to improve its answers to the questions invented by the creative controller. So we have artificial curiosity and creativity in this very, very simple system. At the moment, humans still have more compute and cheaper compute. But every 5 years, computers are getting roughly 10 times faster per dollar. Today, hardware is roughly 1,000,000 billion times faster per dollar. We have greatly profited from this acceleration. Soon, we will have cheap computers with the raw computational power of a human brain, and a few decades after that, if that trend doesn't break, we will have cheap computers with the raw computational power of all 10 billion human brains taken together. And AIs, in this way, will become much more creative than humans are. The previously mentioned adversarial creative system of 1990 was actually just the beginning. Since then, we have produced more sophisticated artificial curiosity systems. And a central idea of these subsequent systems was the concept of compression progress. And all of science is about finding simpler, shorter descriptions of the data. And that's what Newton did and what Kepler did, because general relativity theory was able to predict away the deviations from the old predictions, from the old theory of gravity. Suddenly there was a new, more elegant, simpler theory of gravity, which allowed to very compactly encode many more additional observations. What is simple and elegant in the eyes of one observer may not be simple and elegant in the eyes of another observer that has less prior knowledge, which first needs to be educated to understand the simplicity of the observations, to understand the short rules behind the observational data. And learning here means compression progress. But my formal theory of curiosity and creativity takes into account this subjectivity of the observers. And given this particular observer, some things are easy to understand and elegant and beautiful and simple, and other things are not yet, but they can become so through learning. And this theory of artificial curiosity and creativity really has this learning as a fundamental ingredient, and we can measure this learning progress. And we say this learning progress is the extra intrinsic reward, or the fun. Compression progress not only motivates the scientists, but also the artists. Artists and the observers of art get also rewarded for making and observing novel patterns. Data that is neither arbitrary nor regular in an already known way, but regular in a way that's new with respect to the subjective observer's current knowledge, yet learnable. That is, after learning, fewer computational resources are needed to encode the data. The theory even explains humor. Consider the following sentence. Biological organisms are driven by the 4 big F's: feeding, fighting, fleeing, and mating. Some subjective observers who hear this for the first time think it's funny. Why? as one is perceiving the text, the brain receives a complex input stream. Once you get it, you need only so many bits to store the story. And the difference between before and after, that's the fun that you have.
Thank you, Jürgen. So it has been said that creativity is intelligence having fun. And that's actually one of the questions of can computers, can machines be creative? One of the questions that we're going to touch upon during the Sparks event next year. We're at the end of this conference. Let's call it conference. We are on a stage. And to close, let's see what's coming in 2021 for Sparks, again with CERN's Director of International Relations, Charlotte Lindberg-Warakaule. Welcome back, Charlotte. What's the plan for Sparks going forward?
Thank you very much, Bruno. I think we've had quite an exciting day today, but this is really just a glimpse of what we're planning for next year. But you don't have to wait until September 21 to get engaged. Already today, we're launching an online forum at sparks.cern, where it's possible also to leave questions on artificial intelligence and to engage with the subject. And the most relevant of those questions will inform, of course, the discussions in September of next year. In addition, we're also launching a series of podcasts on artificial intelligence with some of the participants in the forum, so that will also broaden the discussion.
Thank you. Right, and on my end, I would like to thank, first of all, the speakers from CERN and from around the world who have been with us today and have shared their knowledge and their enthusiasm so generously. Most of them are actually going to be with us in a year as well. And then I want to thank the team that has been putting together Sparks. First, the editorial board who has developed the program, and then the production team led by Claudia Marcelloni, who is here in the theater and has been working all these weeks and months to prepare this and plan next year. And I think we have also some partners to thank.
And I want to thank our partners. Sparks is a CERN outreach event, which is part of the CERN and Society Foundation program. These activities would not be possible without the generous support of our partners. In particular, I want to thank Rolex for its long-standing association with the organization. Sparks is also supported by Banque Edmond de Rothschild and the Fondation Didier et Martine Primat and the Geneva Art and Design School, HED Geneva. I thank all of them for their generous support and for their partnership.
Thank you, Charlotte. You can submit your questions and remarks on the sparks.cern website. You can listen to the Sparks podcast, which is going to be launched soon, or you can follow for updates and information the CERN social media channels. Thank you for being with us today. Stay safe, be well. See you next year. Goodbye.